Hi everyone, and welcome to a new video about electric circuits. In this video I would like to discuss a design in an application. And in this specific case we will look at an amplifier design of a voltage amplifier. Of course we will look at the calculations and also verify these in our SPICE simulations. So let's look at the problem, but before we move on we will first discuss briefly what an amplifier design is. Now voltage amplifier specifically, it can be done using an amplifier or operational amplifier component, which is for short op-amp. And that is given here in a symbol. So we have a triangle, it has two inputs and one output. And this input is between these two nodes. It is called the inverting and this is called the non-inverting input. Now we can use this IC for processing of the analog signals. For processing of analog signals and also calculation of our required values, we would like to use a model. And a very simple model of an op-amp can be formed using an input resistance, output resistance, and also the voltage controlled voltage source. And we have seen these dependent sources. So this can be formed like that. So we have again our two inputs, and in between we have an input resistance. And the voltage here, which is controlled by the input voltage here, and that is A times V in, which is a constant. A is some number. And this voltage will be then applied to this R out, which is the output resistance of that operational amplifier specifically. And this node is then that output node. If you connect, of course, here a load, that will be then, of course, the voltage across the load. And this is a very simple model that can be used to, let's say, design an amplifier in any other circuit. If you, of course, use a more complex model, you can add capacitors and other elements in it to have a more accurate results. For analog signal processing, we can also model our transducer, which is, let's say, our sensor that gives the analog signals. And that open circuit voltage of that sensor is the thevenin voltage, and also we have a source resistance, which is then the thevenin resistance. And that is then this circuit. So we have a triangle. Here is that source given here in a shaded region in brown. That's the Vs, which is then our source voltage. And this is the source resistance, which is then given in a thevenin equivalent circuit format. And this is the part where we call the op-amp, where they're using that RF, which is then the amplification part. And the load is then modeled by just a simple resistor. Now this whole thing, including our model, can be then connected to each other. So we can say, okay, we have now our source in the thevenin equivalent format, and we have our op-amp model, and the load is also shown here. And this resistor RF is used to have a negative feedback. That is a theory that is a little bit, let's say, too detailed. In this case, I just assume that we need that and we can use it for our calculations and also design. And this is then the load, just a simple resistor. Okay, let's now look at our specific example. The circuit we will discuss is this circuit. So we will now look at the solutions. What we have actually is first the RS, which is this source resistance of this sensor. And we have an Rin of 50 kilo ohms of this operational amplifier or any other amplifier we have here. The R out is 100, and there is a load of 1 kilo ohms. And there is also a feedback resistor required here, which is not known yet. But there's also an internal gain, that is this A, of minus 10,000 as a gain, voltage gain. You can see volts over volts. So this voltage here, V in, is multiplied by minus 10,000, and it is actually produced here in this diamond shaped source. This is the dependent source here in this model. So what we want is design the circuit such that the voltage gain, G, is VL over Vs is minus 10. So the voltage here across these two nodes must be 10 times or minus 10 times larger than that one, the source voltage. So now before we move on within our calculations, we know from circuit analysis that we need to work out this using, let's say, mesh current analysis, node voltage, or superposition. In this case, I prefer to use again node voltage analysis. So I determine the nodes first. This is a node I don't know the voltage of, so I designate it as X. And this is also a handy node to designate this, and that is also a node Y. So I get X and Y, two nodes. Now next step is actually designating your polarity. So this is the current flowing here in this RS. The IN will go from the point X to ground. And we have also this current flow for RF, which is going from left to right. And we have also current in the load, that is this. And we have also current in R out. So we have actually now 5 arrows here. And we will now develop for each node the current equations using Kirchhoff's current law. So Kirchhoff's current law, KCL, will be now developed for each node, node X. Let's do that first. So what we have is 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 going in this node X and it produces IN and IF. That's actually shown here. Now if I now want to write this down using voltages and resistors, you get this. So Vs, this node, minus Vx or Vin, that's the same, divided by Rs is equal to Vin over this resistor, Rn, plus Vin minus Vl or Vy over Rf. I already actually used Vin, Vl, etc. because we need an expression for Vl over Vs. So I can of course use Vy instead of Vl, but I need to again change that to Vl so that that means actually, and again, an extra step. So that's the reason why I choose directly the load voltage for that. Now, if I now work this out, I can now separate the fractions. So I have then Vs over Rs and then minus Vin over Rs. That's actually for this left part. I do that also for this second part on the right hand side, and I can see that I can collect the terms that have the same variable. So we have a Vin here that can be replaced to the right hand side. Then I get the following, and then take the coefficients together in one parenthesis. So we get now 1 over Rs, 1 over Rn, and 1 over Rf all summed together, times Vn, and then minus Vl over Rf, and that's equal to Vs over Rs. So that's now the expression we have. This thing here, we can now just name that as P, just a letter that will be handy later, and I call this equation number 1. I develop exact in the same manner the node voltage analysis here at node Y. So that means IF here that go in here, it will produce IL and I out. So that's actually here. And if I now again use the voltages and the resistors, I can say Vin or Vx minus Vy over Rf. That's actually over here. So Vy is Vl. And then I out is this voltage minus the voltage here at this node divided by R out. This voltage is A times Vin, so we can just directly use that. VL minus A times Vin over R out plus VL over RL is our load current. All right. Now again, we separate the terms for the fractions and then collect the terms. So Vn over Rf minus VL over Rf, that's for the left side. And again, for this part, VL over R out minus A times Vn over R out and then plus VL over RL. All right, now we have actually the required values. We can now collect again the terms that are the same. So we can say, okay, Vn is here. And we can also place this minus A Vn over R out to the left side. And this VL over Rf can be placed to the right hand side. So we have actually all of the terms for VL and all of the terms for Vn. Okay. What do we do next? Now we can now also place this in a box and call this Q, just a letter. That will be handy again shortly to get that expression in a nice form. And I call this an equation number 2. Okay, now we rewrite now first this equation number 2 as follows. We say Vn is equal to this whole thing, so Q times VL over this part. So that's actually Q over 1 over Rf plus A over R out times VL. We can multiply the numerator and denominator by Rf and by R out, so Rf times R out. Then I get here R out and I get here A times Rf. And in the numerator I get RF times Rout times Q, and then times VL will be then Vin. And this is, of course, much nicer to use as an expression than this one. And let's call this also equation number 3 here. Okay, now we will now substitute this equation number 3, which is an expression for Vin in terms of VL, in equation number 1, because we have an equation or expression of Vin here, and we would like to have an expression where we only have VL and Vs. That's actually our final goal. So let's do that. What we have is Vs over Rs, that's the left side, that doesn't change. This thing, it was P times Vin, that means P times this. That means P times actually this, you see that actually just P in the numerator. And you get again the minus VL over RF, that's still the same. What we now can do is we can now have an expression VL over Vs in terms of the rest of the parameters here. So it can be done after a couple of steps, and to save time I already prepared that for you here, and this is for sure correct. And we have now this expression. Now we will now dive in more detail in this expression and see what's happening when we change some value. Now let's call this also equation number 4 and then move on. First bring up the, let's say, our equations for the P and the Q. That was for the resistors here. And we have this expression determined for the VL over Vs. That is actually also what we need, because while we can insert all the values we have here, and this is of course minus 10, and then we can determine the RF numerically using graphing calculator. That is possible, but I would like to show you more. Let's continue and then use also the Q and the P inside. So just substitute the values here, and then actually take out the RF over RS out of this huge expression, and then we have only Rout plus A times RF divided by the thing here in the brackets, this thing. What you see is the following actually. There's a nice thing to see here. If A, which is the internal voltage gain of this op-amp, is very large, let's say infinite, so 1 million, or very, very large, 100 million, then the following thing happens actually. Then you get actually Rout plus very large number divided by some value, and then also a very large number here. So this numerator and the denominator will be dominated actually by A times RF, and here minus A times RF. So that's actually only, so still we have RF over RS, that is the, let's say, the term in front, that is the multiplication part here, times actually sort of an error, which is then A times RF, when you have very large value for A, divided by minus A times RF. That is actually sort of the limit condition. So if you go in the limit in this expression for A up to infinity, you can see what's happening, and this will dominate and this will dominate here in the denominator. And then we have actually that you lose the RF in the numerator and denominator, also the A and A here, and you will get only minus 1. So the expression is now RF minus RF actually over RS. This is only valid when you have, of course, a very large number for A, and this is most of the time the case for when you use an operational amplifier. The open loop gain of the operational amplifier is in a couple of millions, depending on, of course, the op-amp. It can be also of a transducer amplifier. Then you can use this very simple expression. So I can say, oh, I need minus 10. Let's then look at the expression. Oh, this is already 50, so this is already given. So this must be minus 10, so this must be then 500. So that's just actually done. That is actually our expression, and we can just say this is the result for this design. But if you want, of course, more accurate result, we can just move on. And let's do that. So if I now substitute the values, these are the values, so we can now prove what's happening. Now this is the minus 10, that's the left side. This is RF over 50, so RF is the unknown. That's sort of the X or unknown value in our equation. That is 100 plus minus 10,000, so A is a negative value, so minus 10,000 RF, over, now RF squared, Rout is again 100 over, and this is 1 over 50, 1 over 50,000, so 50k kilo ohms, 1 over RF still unknown, and the rest of the values also from the given here. What you get is then the following. You just first actually divide by 100. So you get 1 minus 100 RF. So you actually also do that here, so you get actually a little bit simpler expression. And now we can move on and say, okay, let's then also substitute this RF squared here in these two parentheses. So one RF in this parentheses, another RF in this. So we get actually 1 over 50 plus 1 over 50,000, this quantity times RF plus 1, this is RF over RF, in a similar form here. So we get actually quantity here times RF plus 1, and this stays the same. Now we can now use these two equations and then solve it. So we can say solve this. Now if you do that, you get the red graph, which is actually minus 10. You can see that. That's actually just the left side. And the blue one is actually sort of this decreasing line, this part. It is actually sort of decreasing because we zoom in this part. And the x-axis are feedback resistance, RF. And this is the voltage gain. And we have an intersection here, which says actually if you solve this, you get RF is 500.72 ohms, so approximately 500. And we already said that using this very simple expression to calculate our RF in this case. So you can see that result and the result from here are very close to each other. But we use this, let's say, more exact expression to get to the more exact value for RF. And we have also seen how much influence these values have. Okay, so if I now, as said before, just use 500, I get my minus 10. But if I use 500.7, I get a little bit larger according to this value or this expression. And I need really this value of RF in order to get the exact minus 10, because there is some error in the, let's say, circuit due to that A, which is not infinite. Okay. Now, let's now look at the next step, which is our simulation results, because I already prepared the simulation. This is the circuit. You can see the RF, the RS, the VS, and also the RIN. This is the voltage control voltage source, which is minus 10K, which is minus 10,000 for A. And here's the R out, and this is the load. Now, if I use 500 instead of 500.7, I get this curve. So I can make a transfer, DC transfer. This is the source voltage that will be changing from 1 to 10 volts. And this is the load voltage will be then also changing. Now you can see at VS of 1 volts, I get VL of minus 9.986 volts. So approximately minus 9.99 volts. So very close to minus 10 times actually as a gain, because this over that will give you approximately minus 10. Now for at 2 volts, as another example, as a data point, you can see this is also producing almost minus 10. And also here, for 4 volts as our VS, and also for VS for 8 volts will get you approximately minus 10 as the voltage gain. So voltage gain is very close to minus 10 for this case. Of course, if you make this 500.7, you will get exactly minus 10. But this is just to show you that the error is very small here. Okay, we can also make another simulation. This is also very handy to see. We can say, okay, what is now the gain if I now change the feedback resistor? Because of course we wanted the minus 10, but is it really the case that I have VL over VS? Now this is the expression. If A goes to infinity, then I have this expression. Now we have several values for RF and also sweeping also the source voltage again from 1 to 10 volts. Now let's see the blue line again. This blue line is actually our situation where we have the RF 500. But if I go to, for example, 200, I see this green line, 200. If I look at, for example, this is at 5 volts. I get from the curve, I get 20. That means my gain is 5 volts I put in and I get minus 20. So I get a minus 4. And this is 200, so 200 over 50 is indeed minus 4. So this is indeed correct. Of course, not exactly minus 4, but it is very close to minus 4. So you can see there is really a linear relationship between this RF and RS. And if I look at different values, for example, this pink, again, at the same value, 5 volts, I get 100, minus 100 volts. And since the pink is 1000, if I substitute here 1000 over 50, I get minus 200. So that means 5 volts times the minus 200 will 200 will give me 5 volts times the gain here, which is then 1000 over 50 is 20, so I will get then minus 100 volts. So this is again a proof that this ratio is correct, not only for this specific value of RF of 500 ohms. Let's also look at the result when we now change the load resistance. That is also, of course, one of the things that can happen. So we have this load again, which is our original case, this blue line again. So 1 kilo ohms. And you can see also the sweep from 1 to 10 volts for our source voltage. And these are the load voltages for 4 cases. Now, I just look at 10 ohms, 100 ohms, and 1 kilo ohms, and also a larger value, 10 kilo ohms. Now, if I look at the blue again, this is again what we have seen before. But if I look at the brown, the green, and the pink one, you can see if the load resistor is very small, let's say 10 ohms here, the difference actually is larger. So it is not anymore exactly minus 9.99. It is now almost minus 9.88. So the error gets larger when you have a smaller load. But when you increase your load, make it 10,000, you can see it is now getting also closer to that minus, let's say 10 volts or minus 10 as the gain. So you can see that here. So increasing the load will increase your accuracy of your gain. That is of course also understandable, because when you have an open circuit, which is a load of infinity, that means you don't, let's say, draw current in your load, and that means the expression is then more precise and also close to ideal. So this is actually just to show you that indeed the load resistance has an effect on the gain. All right. So the voltage gain for different load resistance values has an effect. So we have seen that smaller value and a larger value will produce less accurate and more accurate values for the gain. Okay, let's now summarize everything, because this was a circuit and this was our simulation results to show you that the gain was correct specifically for RF of 500, very closely, and this was just a change in the RF, and seeing also that the relationship for the gain was correct, and this is just to show you that the load resistance change has an effect on the actual accuracy of our gain. Let's now also see that in the actual simulator. So let's now jump to the SPICE simulator and show you how you can generate these plots there also. So let's go to the SPICE simulator and then discuss this further. Alright, we are now here in the SPICE simulator. You can see already that I've prepared the circuit for you. So this is the RS, VS, RIN, RF, 500 ohms, and R out, and this is the voltage control voltage source. If I double click on it, you can see this is the gain we need, and this is the load. So what you can do, you can say, I would like to know what the voltage here is. So you can say analysis, and in this case I just apply 1 volt, so you can also choose another one. So I do analysis, DC analysis, just calculate node voltages, just only the voltage I need here, just my measurement. I get minus 9.986 volts approximately. And of course we want to have exactly minus 10, because 1 volts in must get minus 10 times larger. If I now make this 500.7 was actually the actual value, and again run this, you get exactly minus 10. That's exactly the situation. So this is really the situation when you have this voltage, this resistor here. That is really needed. That extra resistance here is really needed. So extra gain actually, because the loop gain here is not infinite. So that causes actually that you need a more feedback resistor here instead of 500. What you also can do is, if I go back to 500 again, you can also say I would like to have a DC transfer. So you can do that here. And say, okay, I would like to sweep this VS. You can also sweep at different values. And then go from 1 volts to 10 or 8, doesn't matter. And then these are the number of points to make it more accurate plot. If I now make a plot of this, I get the following graph. So for this circuit, I get the following graph. So let me get this a little bit to the left side and also bring this here. So this input voltage is actually really the, let's say, the source voltage. That's really what you put in. And this is the load voltage. Okay, and you can see, if I just click on it with my cursor here, and if I now, for example, select 1, I get the value I already had also in the simulated result shortly. And also I can just look at maybe 5, and this almost minus 50, for example, minus 50 over 5 is minus 10. So again, very close to minus 10 as the gain. You can also do other analysis, like I would like to sweep, for example, the value of the RS and then see what kind of effect it has. I would like to sweep the value of RF or any other value. You can do that using the control object here. So you can just click on this first and then click on a control object you want. For example, if I want to change the RL, I click on it and click on the 3 dots and then, let's say, start at some value and stop at some value and then do the number of cases, or you make a list. You say, okay, I would like to have a list. I would like to start, for example, at 500 ohms and then do 1K and then let's say do 10K and see what's happening. Just 3 cases in this case. Okay, now if I do OK, I see actually a asterisk here. So that means this object or the component will be controlled or will be swept. So we can do again DC analysis and then do transfer, and now I got now 3 curves actually in this case for specific situation, because I have now 3 different values for my RL. So let's see what we have. So you can see there are 3 values and are on top of each other, so it is not really easy to see what's actually going on. You can do the view and then separate curves, and you can see actually the, let's say, the changes more accurately. You can still see, if I now make the label here, this is, let me make this, for example, or make this blue, because that was the case we had. Let me make that blue and make this, for example, a different color. Let me make that green, for example. Now this green is for 10K as a load, and 1K we had, that's the blue one, and there's this brown one or red one, dark brown or dark red, is that 500. So you can see if the, let's say, the resistor is lower, your error gets larger. So if I, for example, click on this one and make the precision larger by going to 3 instead of 2, you can see actually also the precision here, also here the accuracy. You can see also that this is at 1 volts, I get closer to minus 10 volts here for 1K as the load than for the 500 ohm as the load. And also I get more closer actually to the minus 10 volts if I make the load 10K. So this value is larger than that value. Of course a little bit larger, but it is closer to the minus 10. So this is again to show you that you can just play around and see for yourself what the effect is of changing a component value in your circuit. Okay. Alright guys, this is for this example, design example about this circuit using a dependent source and actually modeling a voltage amplifier. And this circuit here, the first part, the VS and RS, was a model for our transducer or our sensor that was applied to our operational amplifier, or our, let's say, our amplifier, which has an RN, dependent voltage source, voltage controlled voltage source, and R out, and this feedback resistor was the question in place here to calculate that to get the gain of exactly minus 10. And the load was also given as 1K kilo ohms. If you have any questions about this example, please let me know. I will try to answer them as soon as possible. Of course, we will move on with more examples, specifically also design, and also later on more examples and videos about electronics, analog electronics, to illustrate the concept in great detail. And we will use, of course, the theory here about electric circuits. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your support and see you next time in another video. Take care.